Today is Monday, November 8th, and we are going to take notes on worksheet 2. So doing some things to learn. As you were leaving, I wanted you to write down some important equations that you derived the last time we were together. And we are going to be on the verge of using those equations after we get done with this worksheet. Okay? So notice, actually, why don't we just write the equations down right now? So do you have your equation sheet out? There are some really important kinematic equations that we have for this chapter. How things move.
Like kinetic, sort of?
It has to do, you're thinking about energy. We haven't gotten to energy. That would be why things move.
Okay.
This is how.
Got it.
So we are studying right now in physics this thing called kinematics. Kinematics is how things move. After we're done with kinematics, which means after this chapter, we'll be done with it, we'll move to dynamics, which is why they move. Okay? Great question. So our formulas, and you have your formula sheet out. Formulas for chapter 3, which will be coming to an end this week. We're almost done with this chapter, so you're going to have a test in this week.
What day? Hopefully not.
I will look it up in a little bit. It's not Friday. We never have tests on Friday, so it'll probably be Thursday.
Good.
But don't quote me on it. Okay, so let's write down our equations. Our first one is average acceleration is change in velocity over change in time. So A is average velocity, average acceleration. And delta V is change in velocity. So that would be, if you're thinking about it, it's VF minus VI. And delta T is change in time. So that would be T final minus T initial. Our acceleration, our label is, I'll put the labels over here, is meters per second squared. Our label for velocity is meters per second, and our label for time is seconds. Okay, our next equation is, I'm going to draw a line, is, can you see green very good? Okay, it is VF equals VI plus AT. VF is final velocity. VI is initial velocity. Ooh, I can't spell initial, sorry.
Is that plus AT?
Yep. And AT means I'm multiplying them. The A is acceleration. Because it's constant, I don't have to worry about it changing, right? Uniform acceleration is the title of our chapter. And T is time. So meters per second, meters per second, meters per second squared, and seconds. So what is the point of this equation? If you know how the initial velocity, and you know the acceleration, and you know how long it's moving, you'll be able to calculate the final velocity. Okay. Then we have VF squared plus VI squared plus 2AX. I want to see how I'll write it for you on your test. Okay. All right. So, sorry, this should be an equal sign. Sorry. VF is final velocity. VI is initial velocity. A is acceleration. Yeah, I did. And X, sometimes you might find a triangle in front of the X. Sometimes you might not. But X is displacement. So your change in position. So notice, what's the difference between this equation and this equation?
There's an X.
There's displacement instead of time. So here is, you can find the final velocity if you don't have time. So you have meters per second, meters per second, meters per second squared, and meters. What's what? So this is an equal sign. Okay. Now remember, you can do algebra and solve for something. So if you know your final velocity and your initial velocity, you can do algebra and solve for how far you're going to go. Right?
Don't you need to find the acceleration too?
Well, if they give you the acceleration, you can do that. Okay. Here, if you have your final velocity, your initial velocity, and your acceleration, you can figure out how long they're moving. Okay. So one more. So here's your, we had a parabola we were playing with last week. We never officially wrote down the equation for that parabola. Sometimes you're going to find a delta sign or a triangle in front of those. Don't be upset if you do. I don't put my multiplication signs in. Are you okay with that? So X is displacement. And that's in meters. VI is initial velocity. Meters per second. T, sometimes you're going to have a triangle in front of it, sometimes you're not, is your change in time. A is your acceleration. That's not going to change. So these are your tools to solve problems. So let's say I don't have T here. What are you going to use to find T? Anybody? Anybody?
Algebra.
No. Do you remember? You used it on the ACT. You want to solve? No.
Okay, what's that? Okay, so
You want to find T, and T's in two different spots, and one of them's squared. What are you going to use? Yes, you're going to use the quadratic formula. Do you remember the quadratic formula? You're going to use it a lot in these types of problems. You don't? B squared plus or minus the square root. No. Oh, that's it. Yeah. Divided by.
Can you say that again? Negative B plus?
That's a disgusting equation.
That's a disgusting what?
Equation.
2AC.
Agreed.
Do you need me to write it down? Okay, we'll do that.
7th grade.
Yeah. That was what
Negative b plus or minus square root of b squared plus 4ac, oops, minus 4ac divided by 2a. So, you would rearrange this, and this right here is your a, right there. That's a. You would rearrange this. This right here would be b. Okay. The t is the x. Your x here, which is displacement, becomes your c in the quadratic equation. Okay?
What's this one called?
This is an equation.
What's it called?
It doesn't have a name.
X is equal to VI.
This right here is how far you moved, if you know how fast you started, and how much time it took, and your acceleration. So you're actually finding the parabola on your displacement time graph, your position time graph. That's all it is. So the computer usually does this one for you. You make the computer do a best fit line. This is what the computer's doing. And this is the equation that it kicks out. And now we're going to use it to solve problems. So you can extrapolate. Maybe you don't have that time on your graph. You can put it into your equation and find out how far you went. Okay? So that's the beauty of that. So you're going to use these for your homework tonight. Okay? Your homework tonight, you're going to use these equations. And then we're going to have you come and we'll whiteboard them tomorrow. Because the math problems that you're going to be doing for homework, that is what normal physics students do all the time. We never do any math problems. Okay, now these are easier than your calculus problems, because we don't have any limits in these. Okay, so those are your 4 equations for this chapter. So let's go to worksheet number 2. So now, I thoroughly confused you. I said initial velocity. There's 2 ways to write an initial velocity in physics, and that is with a little 0. So you could write in your book that v, and that's called v naught, v sub 0 means initial velocity. Bless you. So, you can visualize this because we did this all with the car and the track, right? So, instantly, one of the things I requested for you to do last week was to memorize your scenarios. If you haven't done that, put that down on your to-do list tonight. You need to memorize your 6 situations. You need to know the position time graph, the velocity time graph, and the acceleration time graph for every situation. And actually, there's not 6 to memorize. There's how many? There's only 4. Because the last 2 are 2 together, right?
That'd be 5, Mom.
No?
Because last year were 2 together. Like 1.
Yeah, you got 1 and 2 is number 5. And then 3 and 4 is number 6. So I was right. Okay, so let's look at our little scenario here. And notice we have numbers, so that means that our position time graphs are going to have numbers in them this time. So our position time graph is going to have a number. We're not used to that. Our velocity time graph is going to have a number, and our acceleration time graph is going to be a number. But we already know what they're going to look like because that's what we learned last week and the week before that, right? So we're okay with this. We're comfortable with this. So I have a ball that I'm sending at the top of a ramp, and the ball has an initial velocity of 0, and its displacement is 0. So that means I'm starting at the origin, right? And at x, it's going to have a specific velocity, and at 50, it's going to have a specific velocity. So what do we need to draw in our position time graph that corresponds to the motion of our ball in this problem? So do you have your graph paper?
Yeah.
Oh, I gave you graph. It should look like this. So why don't you get your pencil out? Okay, so we're graphing the situation right here. Get your pencil out, and what should this be? Okay, so draw it with your pencil. And I'm going to draw it with mine. So it should look like this. I'll draw it with my finger. It should look like this. It should just look like a top opening parabola like this. Okay? That's not focusing very well. Whew. Alrighty. Now we're going to take and transition our parabola into a what?
Velocity.
Yeah, what would your velocity time graph be?
Well, it doesn't give us a second,
It doesn't. But what would the general shape be? A straight line like this. So please put that in. Do you understand why it's a straight line?
we didn't put arrows on the axis.
It doesn't say it's stopping. So that's up for debate.
Okay.
It's up to you.
Because
I did not. Because when it gets to the bottom of the ramp, I'm assuming there's a stopper there and it hits it.
it doesn't look like it, though. It just goes
No,
up.
but if it goes onto the table, then that's a different graph,
Right.
right? So I'm assuming it stops, but that's up for debate. So you get to pick. All right, what's the acceleration here?
A positive
A straight
flat
flat line.
A straight flat line.
Get some ruler out.
Okay.
I can't draw straight across. Only up and
Just turn your notebook.
oh, that's a good idea.
So you can only draw straight lines straight up and down, like just turn it this way, and then it's an up and down.
Okay, let's draw the line so we can turn the page. Okay, new scenario. Notice this is not like what we did in our situations. So we have a situation and then we have a flat part. So now we're putting two chapters together. So this was the last chapter and this is this chapter. So first of all, what's going to happen to our ball as it gets to 25? It's going to slow down. So our parabola will look like this, right?
Right.
It'll go like this
Until 25.
until 25. And then all of a sudden, it will what?
Gradual, constant
It would be
increase.
a line like this, right?
Yeah.
So it's going to go like this, and then like that. It's not a flat line.
Then your position's still going up.
Your position's still changing.
Your speed says it.
Your velocity's not changing. So this is the answer here. That, and then this.
It's tricky, man.
That is trippy. Okay, what don't you understand?
Why it's not so.
Okay. The position here is 25. What would be the position here? Guess. No. 25 is right here. What would this be? If this is 50, what? And this is 25, that's not 25. What?
Isn't it that though?
What?
Would be increasing if the thing's straight.
Okay, just answer my question.
I don't know.
You don't know? If this is 50 and this is a number line, this is 25 and that's 50, halfway between is what? What's halfway between 25 and 50? What's halfway? Okay, take 50 divided by 25. Or take 25 and divide it by 2. Do you have your calculator out?
It's like 12 something.
Okay, so add 12 to 25.
I don't know.
37.
37 and a half. Okay, so this is going to be 37 and a half, right? Do you agree? So it's going to be like this. It's rolling along the table. Here it's 25. There it's 37 and a half. And there it's 50.
What is that thing?
It's a
How does
ball.
how does it stay on the top? Is it, oh, there's something inside of the outside.
Yes.
Okay, I was gonna say, how is that like on the top of the rolling? That was tripping me out.
It's a ball. Does that make sense?
Yeah.
So do you understand why the displacement is changing? Because it's like a number line. And every time that goes by, you put a dot on the number line. So then the answer here is this, and then that. Okay, now what's the velocity? We got to break it into two parts. We got the parabola part right here, and then we have Jesse's favorite part, the line that's going straight up.
So it's going
It's gonna be a down slope.
it's
Yeah, so
starting.
it's going down.
So I'm going to divide it in half. So this part is going to be going up, or is it going to be going down?
It's gonna be going down.
Going down.
But you start at 0.
Yeah, but
We
it's
don't-
gonna stop.
Luke, you can't think about position when you're finding your velocity. You have to pick points on your position time graph and ask yourself what question.
Where is it going?
No, what is the slope?
Oh,
And if you pick points on your line and it's the slope, it's this.
yeah. I know it's going to be a negative slope.
Okay, then why did you say what you said?
I just don't know where to put my negative slope. You know what I mean?
No.
I understand what you mean.
I say I know there's going to be a negative slope.
You have to just start at 0. No, you start above 0.
No,
Well, I just
if you
put-
ask yourself the question that I'm asking you, it will not start at 0.
What?
Let's start above 0.
It's going to start above 0.
Because it's increasing.
Okay, so here's our velocity. Here's that, right?
Yeah.
Okay, I'm going to pick a point here. What is the slope of that point? I'm going to draw my tangent line to it. A high positive number or a low positive number?
Oh, positive numbers.
Low compared to this.
That's a high error.
Oh, that's got the high.
So at this point, it's right here. At this point, it's right down here. And at this point, it's that. Did I do a good job of making a straight line? So did I answer your question? Luke? Luke?
Mostly.
No.
I mean, no.
Do you see how it's not 0?
Yes.
Oh, okay.
She's in your head, Luke.
Why don't you ask the answer the question for me?
All right. So I have a line going like this. Now I have to find the slope of this line at each individual point. That it's the what?
It's the same. Like
It's the same,
Above zero.
but it's above zero. So it's like this, right? And that's a straight line across.
So technically, wouldn't like our downward line, wouldn't that just go to the same level that our straight across line is at?
Yes.
Yeah. So the downward line doesn't touch this zero.
No. Because our velocity is not zero, right? So it should look like this. Oh, that's so bad. It's so hard for me to draw. Bless you, Luke. It's so hard for me to draw one when I'm not standing up. Oh, that's so terrible.
You have a ruler right there.
I know. So it would go like this,
The good one.
and then it would go like this. Okay. Acceleration. Which part of this has a slope? The left side. Is it a positive slope or a negative slope? Negative. So you're going to have a line going straight across there, and then it goes to zero.
Is it?
Okay, I'm turning the page. Okay. So now I have a scenario where I have a steeper slope in the first half and a smaller slope in the second half. But we're going from right to left.
Oh.
So we're starting at the top and we're going bottom. We're going to speed up. But we're going to speed up more in the second half.
I'm trying to picture this position time graph though. Yeah.
So what would your position time graph? I'm going to draw mine.
Does it look like this? Like from your angle, would it look like and then that again?
So you think that it's going to look like this.
But we're deep, but we're so. Oh, okay, I got it.
That's not.
No, I don't. I don't think it looks like that. You know, know what it looks like? But what if what if you decreased again? Like what
I
if it was
didn't.
on an even steeper drop? There's nowhere you can like go from that though.
So this, do you agree that this is kind of fast?
Up to 25, I see how it's that.
This one's faster,
Okay.
so it's sharper.
So that's not directly straight up and down yet, is it?
No.
Okay.
So then this would be like this.
And then it gets a little steeper. Right.
And then this would be like this.
I get it.
Does this make sense? Jesse?
I just didn't know how to draw stuff like this. Because didn't we have one of these on like one of our other worksheets?
We did.
Yeah, I just didn't know how to I knew how to draw the velocity, just not the position time.
So I have to erase all my work now.
So next year's doesn't.
Get the answer. Because they might be, need different things. Because this gets easy once you know the answer.
No problem. I wish straight line. But,
Okay, turning page. This one is easy. You've already done this one in your life. You're going up the ramp, and then you're coming back down. So I'm going to let you do this one on your own. Because you can look back at your notes for this one.
Are we just assuming it gets up to 50?
Yep.
Okay.
And then you're going back down.
Got it.
So you can look back at your notes for this one.
Yeah.
Did you say, or for a split second, the ball technically stops?
Yes. Very good at noticing that. Good job.
But it would be too short of a time to like, really notice it. But,
You can definitely pick it up on your sensors because they're so precise.
well, there goes my pretty well drawn half circle.
So this is just a beautiful parabola that goes to this. It flattens out perfectly at 0, a slope of 0 there. So you just have a beautiful parabola. Then this right here, remember, is a line, and this dot right here, exactly at the point where it's flat as a parabola, that's going to be your 0 right here. So you're going to have a nice diagonal line right here. And then this is all going to be negative 9.8. Because remember, this is our falling apple problem. This is what Sir Isaac Newton did for us, besides create calculus.
What was the acceleration?
The acceleration is going to be negative 9.8 straight across. So it'll be a nice straight line right across.
Why did you have to start at 0 for the
Because my slope is really high right here. If I drew a parabola and I found the slope at this point, it's really high, but it's negative because the next one isn't as high. So it's a trend. It's a pattern. Okay? Now I lied to you about doing worksheet 4. You're going to do worksheet 5 tonight. We're going to do worksheet 4 together in class. So you're doing problems with your equations. So that means you need to set things up like this. Every time you have a problem, you draw a picture and you set it up like this. You see that? Every time. So then you can say, oh, I'm missing acceleration, I'm missing x, I have time, and then you can pick which equation you want to use based on the equations we wrote on our formula sheet today. Correct. Because all the equations are derived from each other anyway, right? So. What? It's whatever they give you in the problem.
And I was just writing to it. I wasn't writing
Delta x. Okay, so your job is to study your situations and to do all of worksheet 5. So that means you have 8 problems to do for tomorrow. You have a physics student on skis, you have a goat, you have a dog, you have a car, you have a bus, you have a student dropping a rock, you have a car that has major problems, and then another car. So, dig in. This will be fun. And remember, you're trying, not crying. So you're not leaving anything blank. You're putting 110% in, and you have the rest of the time to work on these problems. So you're working as teams now. We're working together. You can either sit together at the tables in the middle, or you can just talk to each other openly in the room.
Should we have a physics wonder time?
What is your physics? What are you wondering about physics?
I'm just wondering.
Remember,
I know we
that was
do
kind
it.
of-
I know we do
that was
it
kind of-
biology.
that
I
was
must do it
kind
in
of-
chemistry.
I didn't have biology.
I had bio first semester.
So, when we drew that position time graph, when like the speed does increase, like when it started here and then went down and went down for like more,
Yeah.
why doesn't it look like a double parabola, like a
It did. I tried to make a double parabola. It's like two parabolas together, but they're joined.
So the second one's just so skinny that it's hard to tell?
Yeah.
Okay. Yeah, I was gonna say, because wouldn't it look more like that?
Yeah, you have to remember that I'm not good at